So what is the freezing point of a 0.5 molar magnesium chloride solution, MgCl2 solution? And so to set this up, we know we're going to write out our freezing point depression equation. And so it's delta TF is equal to the molality times Kf, the freezing point depression constant, times the Van 't Hoff factor, like that. And so we're looking for delta TF here. We don't know what that is. Equals the molality. The molality of the solution tells us right here it's 0.5. So we have a 0.5 molal solution. Kf is that it doesn't say what the solvent is here, but for the most part, unless I tell you otherwise, you can assume the solvent's going to be water. And remember, for water, Kf is 1.86. So 1.86 degrees Celsius per molal times the Van 't Hoff factor, I. So MgCl2, is it ionic or is it covalent? Well, we just did it before, so we know it's going to be ionic. We have magnesium, an alkali earth metal, with chlorine, a halogen. That chlorine definitely is going to want to steal one of magnesium's electrons, so this is going to be ionic. And since we have one magnesium and two chlorines, Van 't Hoff factor is going to be 3. And so we have 3 right here for this. So if you get out your calculator then, and you basically go ahead and say that we have 0.5 times, whoops, my calculator's being a little iffy here. So times 1.86 times 3. And when you do that, I get 2.79. And so in this case right now, my delta TF is going to be 2.79 degrees Celsius. Now, it asks for not the change, but asks what the freezing point is. Now, water's normal freezing point is 0 Celsius. And this is a freezing point depression up here, which means that freezing point will be dropping. And so if it starts at 0, drops by 2.79, the temperature now, the new freezing point, will be negative 2.79 degrees Celsius. Since we started off, though, with 0.5, one significant figure here, then it means our final answer here for the freezing point is going to be negative 3 degrees Celsius. Just as a quick note here is that looking at significant figures, we said before on this that our 0.5 has one sig fig right here. The 1.86 is a constant, that therefore it has infinite significant figures. The Van 't Hoff factor, your I right here, it's got to be a whole number. You can't really have can't say something breaks into 2.5 pieces or something like that. And since it's got to be a whole number, it's basically a counting number, is that it's also considered to have infinite significant figures, because the fact that is this about 3? Does it break into about 3 pieces? No, it breaks into exactly 3 pieces. And so the only thing that's really going to affect our temperature calculations here is going to be that initial molality, or whatever we have to do to figure out that molality, if that's the case. So we get negative 3 degrees Celsius as our freezing point of our 0.5 molal magnesium chloride solution. So let's look at another one down here. How many moles ammonia must be added to 70 grams water to lower the freezing point by 1 degree Celsius? And so to set this up, we're going to say the same thing we did before. You know, delta TF is equal to mkfi. And so do we know what the freezing point depression is? It says we're lowering the freezing point by 1 degree Celsius. So we know this guy is just 1 right here. The molality, does it tell us molality? No, it really doesn't. It says how many moles, but we don't know that. So that's our molality times Kf. And so we have to look at what the solvent is. The solvent here is water. And so when it's water, 1.86 is our value for Kf, times I. How many pieces are it going to break into? So what's our solute? How many moles of ammonia? Ammonia is NH3. NH3, is this going to be ionic or covalent? If you look at it here, is that ammonia, nitrogen sort of towards the middle here. It's sitting over there in column 5A with hydrogen. If you notice, it's also one of those sort of out of order. You normally expect the hydrogen to be first. This is definitely going to be a covalent one. This is not an ionic substance, and since it's not ionic, it has an I value, a Van 't Hoff factor of 1. And so solving for this, if we want to solve for the molality, we'll divide both sides by 1.86. And so doing so, we get that the molality of this substance, if you break out the calculator, 1 divided by 1.86 ends up being 0.538 molal solution. And so does this answer our question? The question is how many moles? Not yet. So we're going to have to say our molality, 0.538. We're going to put this into our molality equation. And remember that the molality of a substance is equal to the number of moles of that substance, which we don't know. So we're going to call X moles of ammonia on top, divided by the number of kilograms of solvent. And in this case, we have 70 grams of our water, of our solvent. And so 70 grams is 0.07 kilograms. And so to solve this here, we're going to multiply both sides by 0.07. So we take our 0.538, multiply times 0.07. Doing so, I get a total for X of 0.0, it's equal, 0.03766 moles of ammonia. Significant figures here. 70 grams has 1 sig fig. Our temperature has 1 sig fig, so we'll round this to 1 sig fig. So our final answer here is 0.04 moles of NH3 of ammonia. And so that is how you'd go about doing some freezing point depression calculations. 7 grams of NaCl, sodium chloride, are added to 2 liters of water. What is the boiling point? And so we know that we're going to end up having to use our delta TF is equal to, we said, the molality times the boiling point, not TF, TB. It's boiling point we're looking for here. Delta TB is equal to M times KB times your Van't Hoff factor I. And so that's what we've got right here. Do we know what the change in the boiling point is? No, we don't. Doesn't say anything about that except for that's what we're looking for. So delta TB is what we have here. The molality of the substance, says we have 7 grams of NaCl are added to 2 liters of water. Doesn't tell us the molality directly, but we can figure it out because molality, remember, is moles of solute over kilograms of solvent. And so we have how much NaCl? That's our solute. We have 7 grams. And so this is one of these cases where we're going to want to set up our table here, 7 grams NaCl. Set up our table going across here. We want to cancel out grams. We want to go to moles. To find that conversion, we're going to have to go over to the periodic table. And looking at that, we look at that sodium is 22.99. And so we take 22.99, which so 1 sodium plus chlorine, which looking at that up, you can see it's 35.45. And so from that, we get 58.44. And so we have 58.44 grams in 1 mole. And so to figure this out moles, we'd say 7 times 1 divided by 58.44. And we end up with 0.1198. 1198 moles divided by the number of kilograms of water. And in this case right here, we have 2 liters. A liter is 1,000 milliliters. And remember, water has a density of 1 gram per milliliter in normal cases. And so 1,000 milliliters would be 1,000 grams. 1,000 grams is 1 kilogram. And so if I have 2 liters of water, that's just 2 kilograms of water. So it's this nice little thing to remember here. If you ever have a liter of water, that weighs a kilogram. 2 liters of water, that weighs 2 kilograms. And so that's what we've got now for our molality. Times Kb. Kb, since we are talking about we're adding this to water, it means we're going to use the ebullioscopic constant, or the boiling point elevation constant for water, which is 0.512, and then times the number of pieces it wants to break into. NaCl is definitely ionic, and so it's going to break into 1 sodium and 1 chlorine for a total of 2 pieces here. And so we take a 2 right here. And so if we go ahead and we work this out, we would say we have our 0.1198 divided by 2, then times 0.512, then times 2 on that. And so I get 0.06 if I am doing that right. And so I get in this case for a total of delta TB. Not a whole lot of raising in the temperature, which sort of makes sense. We only added 7 grams of salt. 0.0613 degrees Celsius. Now, for our significant figures is that, the 7 over here, that's infinite. The 2 liters, though, has 1 significant figure, and that's going to sort of affect our things. So remember, our 0.512 and our 2 for our I don't really make a difference. So this is going to be rounded to the hundredths place here. But the question asks you what the boiling point is. So to find the boiling point, though, we have to look at the original boiling point of water, which is 100 degrees. And that 100 degrees is sort of defined to be exactly that. That's what we're doing for the purpose of this class. And so if it's exactly that, then when we add our 0.06 to the 100, is that the 100 really isn't going to matter significant figure-wise. The only thing that's going to matter is going to be our 0.06. And so since that's rounded to the 100th space, then our final answer is also going to be rounded to the 100th space. And so once we get an answer here, your final answer would be 100.06 degrees Celsius would be our final answer here. Because of the fact that our 0.06 is rounded to the 100th space, and so when we add that to the 100, which is exact, the 100 doesn't affect it, we just end up with 100.06 degrees Celsius for our new boiling point of our salt solution, our very, very dilute salt solution. So that's how you'd work that out. Next question. A sloppy chemist neglected to label a 3.0 molal iron chloride solution with the iron ion used. If the solution was found to have a boiling point of 104.6 degrees Celsius, what ion of iron was used? Remember that iron comes in two flavors. For its ions, it's either iron 2 or iron 3. And so remember, whenever we're writing these out, we wouldn't just want to write iron chloride. You'd want to write iron 2 chloride or iron 3 chloride. And in this particular problem, our chemists made a mistake, and they did not put that on there. They should have, but they didn't. So let's try to set this up. It's the way we're going to find out which type of iron ion is. We're going to basically boil it and look at what the boiling point is. And that's going to let us figure this out. And so let's take a look at how we do that. So it says we have a boiling point of 104.6 degrees Celsius. Since this is in water, we know the normal boiling point of water is 100. And so then delta TB, the change in the boiling point, would just be 4.6. And so we say 4.6 is going to be equal to the molality. Do we know the molality? It tells us right here. Don't have to calculate it. So it's a 3.0 molal solution times Kb. And since we are dissolving this in water, Kb will be 0.512. And Van 't Hoff factor. We got a little issue here because if this is iron 2 chloride, then this will be FeCl2. If it's iron 3 chloride, it'll be FeCl3. We don't know which one of these this is. FeCl2 breaks into 3 pieces. FeCl3 breaks into 4 pieces. So we really don't know what I is. So I guess we're just going to solve for I here. It's the only thing we're missing anyway. And so to do this, we'd want to basically, to solve for I, just take 4.6, and from that, divide that by 3.0, and divide that by 0.512. And so we take 4.6 divided by 3, and then divided by 0.512. And in doing so, I get 2.994 from my value of I. And so if I equals 2.994, that's pretty much, remember I has to be a whole number. It's pretty clear that's going to be 3 for our value of I here. So I has to basically equal 3. And if I equals 3, I have my two choices. Is it FeCl2 or FeCl3? FeCl2 would break into 3 pieces, while FeCl3 would break into 4 pieces. So we know that it has to be our FeCl2 over here. That's got to be what we're dealing with here. And so if it's FeCl2, then this has to end up being iron 2. So iron 2 chloride. And so the ion of iron here would be just Fe2+. And so that's how you'd work that out. That's a little more of a non-standard one, but what you can see is that you can use these techniques to find things that otherwise you might not be able to get to easily. And so that's basically how you'd work out some basic boiling point elevation problems.